Hello, welcome back to Statistics and Mathematics YouTube channel. Today we are going to continue our series of videos on probability theory. And today we are going to tackle what is termed as probability functions. We have two types of probability functions, that is the moment generating functions and then characteristic functions. Today we are going to tackle what is termed as the moment generating functions, and in our videos to come, we are also going to tackle what is termed as the characteristics functions. So what is termed as moment generating function? Moment generating function is a function that generates moment, right? So for instance, let's say for the probability distribution that we have, those of us who have been able to learn ahead of this course, you come across probability distributions, right? We have discrete probability distribution and then continuous probability distribution, of which we have binomial, Bernoulli, Poisson, exponential, gamma, beta, normal distribution, and many more. Upon all these distributions that we have, we can generate unique moment for this particular distributions. So the moment generating function, as basically has been explained to us here, is a function that generates moment, right? Yes. So mathematically, how can we define moment generating function for a particular random variable? We are saying that the moment generating function of a random variable x is denoted by this one, right? And then we are going to say that this moment generating function with random variable x can be expressed as expected of e raised to the power t of x, right? So you see this x here was the random variable that we see here. The random variable here was x. So if in case in any example or in any question you see the random variable to be y, instead of the x here, you are going to turn that place to be y, and that is going to affect here to be y, right? So it's not always going to be x, right? We are treating x as a random variable, so take note of that. So here we are just saying that the moment generating function of the random variable x, as you can see here, is equal to the expected of e raised to the power t of x, right? So since when we were treating the random variable, we were able to define the types of random variable, that's the discrete random variable and the continuous random variable, and then in redefining that, we're able to calculate for the expectation for the discrete random variable and the expectation for the continuous random variable. And then we learned that for the discrete cases, we said the expectation of x is equal to the summation of our x moving from 0 to infinity of the random variable times the probability function, right? That is how we can calculate for the expectation for the random variable x in a discrete case. For the continuous case, the expected of x will be equal to integral moving from negative infinity to positive infinity of x times f of x, dx. So that is what we are having here. So as you can see, that's for the discrete and the continuous case. So we are going to define how we can generate moment for both the discrete case and the continuous case. So I was just using this one, the discrete random variable and the continuous random variable, as an example for you to really appreciate what I'm going to discuss here. So you can see that when we had expectation of x, when we come to the summation sign, here is x. When we have expectation of x, when we come to the integral sign, we are having x multiplying the function. So here, the moment is just telling us that we should let our expectation of x, right here, this expectation of x, we want to represent our x to be e raised to the power t, e raised to the power t of x. So we are just representing our s to be this. So anywhere we see x, right, we are going to just replace e raised to the power t of x, right? And that one will give us the moment generating function, how we generate moment generating functions for both discrete and continuous cases. So here, when we come here for the discrete cases, you see here was x, right? So we are just representing our x here to be e raised to the power t of x. So here we are going to replace here to be e raised to the power t of x. Once you replace by e raised to the power t of x, we are going to get the discrete case, how we generate moment for discrete case. And when you come to the continuous, when you replace the x by e raised to the power t of x, we are also going to get how we generate moment for continuous case. So basically, that is the mathematics behind the moment generating function. So let's dive into examples for us to really better our understanding on the moment generating function. So here, a discrete random variable y has probability mass function given by this one, right? There is the probability mass function. So more or less, Our random variable here is y, right? You shouldn't forget. So when we are defining it, we are going to define it in terms of y. We are not going to use x. And then there's our function, right? Our function, p of y. So p of y will be represented by f of what? Y, right? So he said we should generate moment for what? Sorry. We have learned that we should generate moment. We should generate moment for what? Y. So that one is in terms of discrete case. And then we just learned that for discrete case, right, our moment to do what? Summation moving from y moving from 0 to what? Infinity, e raised to the power t of y times f of what? Y. That is what we just learned. But we should know that our y is moving from what? 0 to what? 12. So we are not going to move from 0 to infinity, but rather 0 to what? 12. So we will come back and redefine that. So we are going to get summation y moving from 0 to what? 12. E raised to the power t of what? Y. Because that is what we just said we are going to do. We are going to multiply by the function. And this is what our function f of y, of which we are going to get 12 combination y times 0.6 raised to the power y times 0.4 raised to the power 12 minus y. So this is what we have, as you can see here. This is what we are having here, right? So I have the solution there. I want you to really appreciate it. So let's dive into the solution on the slide so that we can go faster. So here, this is where we're able to do up to, right? So we have multiplied e raised to the power t of y by the function, right? So you could see that we are having y here, and then we are having y here. So that means that we can multiply. So when we multiply, we are going to get 0.6 times e raised to the power t, right, or raised to the power y, right, as you can see here. So we just multiply through. So when we multiply through, this is what we are going to get. And if you try to expand this one, when you try to expand it, it means that anywhere you see the first one, we are going to set our y to 0, right? So we are going to set it up to what? Y is equal to 12. So we are going to do y is equal to 0, right? Probability that our y is equal to 0 plus probability that our y is equal to 1 plus probability that our y is equal to 3 plus plus probability that our y is equal to what? 12, right? So this is what we are going to do. We are going to do up to probability that y is equal to what? 12, right? So the moment you keep on expanding this one, right, this represents the sum of what? The binomial what? Expansion, right? This represents the sum of binomial what? Expansion. And then we learn from our elementary calculus class and then our elementary school that the binomial expansion, right? The binomial expansion, we are going to have something like, I'm coming. We are going to have something like a plus what? B raised to the power what? N. This represents the binomial expansion. So we are going to deduce our a, our b, and then our n from what? This expansion to get this what? Format. And from this expansion, this place will be what? Our a. This place will be what? Our b, right? And then the 12, as you can see here, will be what? Our n. Since we said our y moved from 0 to 12, so our n here is what? 12. So let's come and put it here to get our binomial expansion. So when we come here, we are going to get our final answer to be 0.6 e raised to the power t plus 0.4 all raised to the power 12, right? So that is what have been what? Explained what here, basically. So here, this is what the summary for the moment generating function for that question that was posed above. So let's go to the next question. It says a continuous random variable y has a probability density function given by f of y is equal to 4 times e raised to the power negative 4y, where our y is greater than 0 or 0 what elsewhere. And we have been asked to find the moment generating function if our y is a random variable, right? Yes. So here we all know for the continuous case, we just learned for the continuous case that here we are going to integrate from negative infinity to what? Positive infinity of e raised to the power ty times f of y, right? And then when we come here, we are saying that our y is greater than 0. So this one, we are going to move from 0 to what? Infinity. So this is the whole formula. But for this one, we are trying to solve the question. Since we said our y is greater than 0, right? Times So here will be e raised to the power t of y times f of y. So f of y will give us 4 e raised to the power negative 4y. So that is what we have, and we are going to get 4 e raised to the power negative 4y plus t what y. So that is what we are having, right? So we can do more factorization. We can factorize negative 4 y out, and we are going to get integral moving from 0 to what? Infinity of 4 e raised to the power negative y t minus what? 4, right? So this is what you are going to have, dy. And we are going to solve this one to get the moment generating function for the function given what above. I have the solution there. Let's go inside to solve to really understand what we are doing here. Yes, so this is where I was able to explain to, right? So if you do the integration very well, you are going to land on an answer 4 divided by 4 minus t, where our t is strictly less than what? 4, right? Yes, because if our t is equal to 4, you are going to get the function to be what? Undefined, right? So let's dive into this theorem. This theorem is a very nice theorem for us to really understand when we are given a moment generating function and then we are asked to calculate for what the expectation for the moment generating function. How are we going to calculate for the expectation? How are we going to calculate for the variance? This theorem is really going to help us to really appreciate it, right? So he is saying that the theorem is saying that if our moment generating function for the random variable x exists, then for any positive integer k, right, if you take the derivative of the moment generating function with respect to what? K, and with respect to t, right, and put t is equal to what? 0, right, we are going to get what? Expectation of what? X raised to the power at k, right? So here we are differentiating it with respect to what? We are differentiating it with respect to what? K, t, right? Yes, so the moment you take the first derivative, right, the moment you take the first derivative and then put t is equal to 0, right, we are going to get expectation of what? X, right? So here, let me break it down for you to really understand. So when you take the first derivative of the moment, right, you are going to get expectation of what? X. If you take the second moment, if you take the second derivative, you are going to get expectation of s squared. If you take the third derivative, right, you are going to get expectation of s cube, right, dot 2. When you take when you take the derivative with respect to what? K, right, of x, you are going to get expectation of what? X raised to the power k, right? So that is what the formula is trying to achieve here. So how can we prove this one? We just learned from in this video that we said that the moment generating function for the random variable x is given by expected of e raised to the power t of what? X. So if I'm taking the derivative of this function, the first derivative for this function, I'm going to get expected of what? X e raised to the power t of what? X, right? And I'm going to put t is equal to 0. The moment I put t is equal to 0, we are going to get expected of what? X e raised to the power 0. And then here we are going to get expected of what? X times 1. You see that the first derivative have given me expectation of what? X, right? If I take the second derivative to, let's take it, and you will see that we're going to get expectation of what? S squared. So for that one too, we are going to take the first derivative, right, of this function. So here we are going to get x e raised to the power t of what? X. So let's take the second derivative of this one. We are going to get, we are differentiating with respect to what? T. We are going to get s squared e raised to the power t of x. So put t is equal to 0, we are going to get expectation of what? S squared. So all that the theorem is trying to tell you that when the moment generating function is given to you and you take the first derivative, you are going to get expectation of x. When you take the second derivative, you are going to get expectation of s squared. When you take the third derivative, you are going to get expectation of s cube. When you take the fourth derivative, you are going to get expectation of x raised to the power 4, right? If you take the kth derivative, you are going to get expectation of x raised to the power k of that moment generating what? Function. So let's dive into some question solving for you to really understand what I'm trying to explain. So for this question, it says a random variable y has a moment generating function, right? A moment generating function, and that moment generating function is what we solved, the example we solved earlier. So we have been asked to calculate for the expectation of y and then variance of what? Y, right? So this is what it has been given to us. So let's try solving it, right? So first, all that you are going to do is what? Just take the first derivative of this one and then put t is equal to 0. So how can we take the derivative of this one? Let's do it. The first derivative of that one will give us 12, 0.6 e raised to the power t plus 0.4 raised to the power 11 times 0.6 e raised to the power t. Just put t is equal to 0, and we are going to get 12, 0.6 e raised to the power 0 plus 0.4 raised to the power 11, 0.6 e raised to the power 0, and we are going to get our answer to be 7.2, right? 7.2. So I have the solution here. So here is the solution, right? We are getting our answer to be 7.2. So when we take for the variance, right, we know that variance of y is equal to expected of y squared minus expected of y all squared, right? So we need to find expected of y squared, and if we want to get expected of y squared, we have to take the second derivative of y. So here we are getting 12 times 11, right? If you take the second derivative of the function, we are going to get 12 times 11 times 0.86 e raised to the power t plus 0.4 all raised to the power 10 times 0.6 e raised to the power t squared plus 12 times 0.86 e raised to the power t plus 0.4 all raised to the power 11 times 0.6 e raised to the power t, right? And we are going to put our t is equal to 0, and we are getting 54.72, right? So that is what we are getting what here. And then for the variance, it will be very, very simple for us. Yes, because we have expectation of y squared. Expectation of y squared is what? 54.72 minus expectation of y all squared. That is 7.2 squared. And then once you do the subtraction very well, you're going to get 2.88. Yes, that is that for that. And then for the continuous case, he said a continuous random variable y has a moment generating function given by that, right? And then we have been asked to calculate for the expectation of y and the variance of y. So what that we are going to do for the expectation, first derivative and put our t is equal to 0, right? So here this moment generating function, we take the first derivative, we have 3 into bracket 3 minus t all raised to the power negative 2. We are going to put our t is equal to 0. When we put our t is equal to 0, we are getting our expectation here to be 1 over 3, right? Let's take the second the second derivative, and we are getting 6 times 3 minus t all raised to the power negative 3. And when you put t is equal to 0, we are getting 2 over 9, right? Yes. So for the variance, we are just going to have expectation of y squared minus expectation of y all squared. And when you substitute it inside, we are getting 1 over 9. So that is that for the moment generating function. In our next video, I'm going to discuss to you what is termed as what the uniqueness theorem in moment generating function, and some essential theorem that we can use when solving moment generating questions. So don't forget to watch that video, because if you watch it, it's going to also give you more light on the moment generating function. So please, this is Statistics and Mathematics YouTube channel. Kindly subscribe, like and share, so that this video will get to your friends, for them to also better their education life in probability theory. Thank you for watching. Bye.